Hey everyone, thank you for the opportunity to share our project. My name is Omer and I'm a master's student at Tel Aviv University in Israel. I'm doing my research in Ron Shamir's lab that specializes in bioinformatics and electronic medical records analysis. And today I would like to tell you about a joint project that we've been doing throughout the pandemic, which highlights how machine learning can be utilized to address clinical challenges. So in early March, the pandemic was already coming to Israel. Here is a view of the pandemic in Israel in terms of daily cases across time using weekly averages. So you can also see our three waves, where the third wave was recently dramatically going down due to the vaccination process that began in late December. But most of the story I'm going to tell you today is about this period until last December, during the first two waves and during full lockdown. So back in March, after the first cases were confirmed, we started to think about how we could contribute. So we wanted to build a model or a tool that has the potential to improve patient care. And there was evidence that early treatment may prevent clinical deterioration in COVID patients. So we came up with the problem of identifying who is likely to deteriorate among hospitalized patients. So we decided to provide a decision support to clinicians, a validated model for detecting which patients are at risk for clinical deterioration. Such a model can improve patient care by preventing condition worsening, and also it has the potential to improve resource utilization at the ward level, like by anticipating the need for mechanical ventilation. So to define the deterioration criteria, we used a modified version of a prognostic score called the National Early Warning Score 2, or NEWS2, which is a commonly used clinical risk score that incorporates several physiological variables, as you can see here. And after the pandemic emerged, a research group from China suggested a modified version for COVID patients. So this modified version adds the age factor to the formula, and it was broadly used worldwide. So scores are computed by summing the points for each category, and we end up with three aggregated risk grades representing low, mild, and severe conditions. And according to our records, we confirmed that higher modified NEWS scores were associated with higher mortality and ICU admission rates. So we use the threshold of modified NEWS score greater than 7 as the deterioration outcome, but also different cutoffs can be easily defined. The problem, of course, is that this is a new disease, and in this period, we had no public personalized data from other countries. So actually, in the period before the COVID outbreak, we were already in a collaboration with the Tel Aviv Sourasky Medical Center for the analysis of infectious disease. So we leveraged our collaboration and experience working with them and started analyzing personalized data of hospitalized COVID patients in real time. We later also initiated additional collaboration with the Shiva Medical Center, thus collaborating with the two largest hospitals in Israel. So we used the electronic medical records stored in both hospital systems. And in order to create a robust model, we used only standard objective features that are routinely captured as part of clinical care. So the data contains various types of health records, and the high dimensionality of the data could be valuable for machine learning modeling. So we framed our problem in a machine learning context as a multivariate time series classification problem, where we are given a prediction for deterioration at each time point t using both baseline and longitudinal data. So the prediction were made for the next 30 hours in a sliding window approach. And as deterioration can be usually anticipated by a clinician several hours in advance, we decided to exclude observations from the 6-hour period prior to the event. meaning that all of our predictions are made at least 7 hours in advance. Additional basic information about our data split. So we use data from the Shiva Medical Center for model development, and the data from the Tel Aviv Sourasky Medical Center was used for external validation. Now I'll briefly present our general pipeline for this prediction task. So we'll skip the first 2 steps of cohort selection and time series discretization, but they're detailed in our paper. And note that throughout the model development, we worked with domain experts and discussed over multiple subjects, like defining our inclusion and exclusion criteria. So we performed feature engineering for 21 dynamic features that were reported as risk factors for severe COVID, such as D-dimer and oxygen saturation. And we were looking at features that capture the temporal behavior of the data. So we constructed summary statistics over historical time windows of different sizes. And in addition, we were interested in features that capture recent data patterns and interactions between variables. Eventually, about 500 features were extracted in total after excluding some features with high missing rates. Now, one of the greatest challenges with electronic medical records is the large amount of missing values in labs and vital signs. So as part of the pre-processing steps, we perform data imputation for all variables and all patients at each time point. Specifically, we use linear interpolation for imputing missing data. And then for the remaining missing values, we use the mice approach, which is a commonly used algorithm that models each feature with missing values as a function of the other features. To handle the high dimensionality of our data, we examined 2 strategies for feature selection. The first strategy selected the features with the highest correlation with the target. And the second strategy used feature importance as calculated by XGBoost, a gradient boosting trees algorithm. So we actually chose the second strategy for our final model, and specifically, we trained XGBoost on the full training dataset, and then we used the computed feature importance score to select the top 100 features out of our 500 features. So we evaluated several supervised machine learning algorithms for this prediction task. All of them were tested in cross-validation on the training set. And finally, we chose CutBoost, the gradient boosting trees algorithm, as our final prediction model, as it achieved higher performance. So the results showed good discrimination, achieving area under the ROC curve of 0.84 and a high value of area under the precision recall curve of 0.74, where all the prediction refers to events at least 7 hours in advance. To assess the contribution of each feature to the final model, we used CHEP values. So the top 20 important features of the final model are summarized here. So we can see age, arterial oxygen saturation, maximal LDH value, and the standard deviation of body temperature as important features for our prediction task. To test the model on an independent patient cohort from a different hospital, we used the second dataset from the Tel Aviv Sourasky Medical Center. So the test demonstrates comparable results with a slight decrease from the development dataset, which can be expected as distributions between different institutes can shift. And in addition, this slight decrease can be also explained by the lower temporal resolution of this dataset compared to the development dataset. So we have several future directions, of which some are already in advanced stage. We are developing models for early warning of additional outcomes, such as oxygen deficiency, ICU admission, and mortality. Also, we are going to extend our design to a multi-center training, not only a single center. And we are already working with additional Israeli hospitals for that goal, called Asuta. We plan to extend our existing cohort by adding more features and adding more patients. And actually, we collected so far data derived from around 6,000 patients. We assume that there are differences in the characteristics of patient cohorts across different periods. So we are also interested in a comparative analysis across the different COVID waves. And finally, we plan to perform existing model benchmarking, and we already implemented several models from previous work for that goal. To sum up, we introduced a machine learning model for predicting deterioration in COVID patients for the next 7 to 30 hours. We don't use the data from the 6-hour period prior to the event. Our model generates repeatedly updated predictions during the hospitalization, so it actually addresses the temporal dynamics of the disease and allows tailored patient therapy. We utilized robust external validation using data from a separate hospital, and we have several future plans for extending this project. And with that, I would like to acknowledge my collaborators, and especially to my research partner, Dan Koster, and my supervisor, Ron Shamir. Thank you for listening.